Good morning, everyone. We're gonna finish off the notes today, and then I've got a problem set on Google Classroom that I want you to start working through. You can work in groups for that, but we'll probably be working on that for the end of this class and a portion of our next class. And then I'll make a second problem set, and we'll probably be working on that when I come back. So, this last part of the notes is very similar to the conservation of energy part. So just like we've got conservation of energy if there's no work being done on the system, if there's no outside forces that are acting on a system, then momentum is conserved. So in the absence of, I'm going to say, external impulses, okay, we could also say external forces. That would be okay as well. But really what matters is the impulse. So if there's impulses that we can essentially ignore because they happen at a very quick time or because they're really small forces, then we can say that our momentum is conserved. In general, the cases where this happens or the cases where we assume this are during collisions and explosions. So that's the interesting physics for conservation of momentum. That's where it's most often used. Because this happens in very little time, both of these events are very sudden, so either something runs together or breaks apart. Because it's a very small amount of time, the impulse exerted by an outside force is going to be very small. So you can imagine that being from gravity, right? You've got some force of gravity that's constant, and then if your time is really small, then your impulse will be really small. So we can essentially ignore the impulse from gravity. And then our two conservation things, so conservation of energy and conservation of momentum, are the basis of, they're the fundamentals of experimental nuclear and particle physics. So there's physicists right now who are running equations that are saying, momentum going in equals momentum going out, and energy going in equals energy going out. And that's how they figure out all this stuff about collisions happening in particle accelerators, everything like that. They'll set up a bunch of detectors and they'll detect some stuff, and from that, so they'll have a target and they'll shoot stuff really, really quickly at the target. It'll break something apart, and then its parts will hit a set of detectors, and from that set of detectors they can figure out how much energy they hit them with, and then using conservation of energy and conservation of momentum, they'll figure out what mass and what charge those particles have. They can do research into what are protons made out of, what are subatomic particles made out of, what does a nucleus have, what's the structure of a nucleus, things like that. But it's all based on them being able to do conservation of energy and conservation of momentum. So they'll program that into their computers when they're doing the calculations. The general statement for this is that our initial momentum equals our final momentum. When we have one object in the problem, this is really trivial because we just have mv initial equals mv final. But in most cases, there will be more than one object on at least one side of the equation. In these cases, so this is the general case, our rule states that the total initial momentum equals the total final momentum. So we have to add up all the momentum at the beginning. That'll equal all of the momentum at the end added up. We can also write this as this. So this is that same statement, just in math. It says the sum of the initial momentum equals the sum of the final momentum. Okay. For these problems, it's going to work best to use the problem-solving framework. So I expect you for the problem set to use the problem-solving framework we went over at the beginning of last semester. It's also very important to draw axes on your picture so you get the correct signs on your values, because we have to call some direction positive and some direction negative. Okay. So, here we go. I'm going to go through these example problems, and then I'll say a little bit about Maybe I'll get to that in our next class. But I'll go through these 4 example problems, and then I'll tell you, sort of what is on the problem set. So here we go. David and Mark are in bumper cars. David plus his bumper car have a total mass of 110 kilograms. Mark plus his bumper car have a total mass of 130 kilograms. David speeds towards Mark at 9 meters per second. When they collide, David comes to a stop. How fast does Mark move after the collision, assuming he was at rest at the beginning? Okay, so for the picture here, I'm just going to draw David. He's going at Mark, and then after the collision, it'll be Mark is moving away, and David will be still. Okay. What I'm looking for is Mark's final velocity. So I'm going to say Mark, or velocity, final of Mark. Okay. We're going to have to label, we're going to have to put 2 sort of subscripts on our velocity because we have 2 different velocities in play. We've got David's and Mark's, and we've got both the initial and final. So we need a letter to indicate each one of those things. The things that we know the initial velocity of Mark, we know the initial velocity of David, we know the final velocity of David. So this is 0 because Mark starts at rest. The problem tells us that David starts at 9 meters per second. The final velocity of David would be 0 because when they collide, David comes to a stop. So that says that David is going at 0 at the end. And then we've got the mass. So M for David is going to be 110. M for Mark is equal to 130. So we've got a lot of things to keep track of. Once we write it all down, though, it's not too bad. Our equation that we'll use is conservation of momentum. So we're going to say sum PI equals the sum of PF. Okay, so the PI would be, we're going to add up Mark's and David. So we'd say M mass of David times V initial of David plus mass of Mark plus VI, or times VI. Mass of Mark times VI Mark. So that's our initial momentum. Again, mass times velocity for both of our people at the beginning. And then that'll equal MD VFD plus MM VFM. All right. So this is, again, just our equation here. This is for David, for Mark at the beginning, David and Mark at the end. Now I'll plug in my numbers, and a lot of them will be 0, so that'll be good. So David VI would be 110 times 9 plus 130 times 0 is equal to 110 times 0 plus 130 times VFM. That's what we're looking for. Okay. That's got a 0 in it. That's got a 0 in it. So we can cross those out. I do 110 times 9. Let me turn this on. 110 times 9. 990. That's going to equal 130 VFM divided by 130. I get 7.6. It's a velocity, so it's going to be meters per second. That equals VFM. Okay, so because David and his bumper car were lighter than Mark in his bumper car, David goes in faster, but Mark doesn't leave with as much speed as David comes in with, because momentum is conserved. So since Mark is lighter, he has to have a bigger mass, or bigger speed than Mark, who is heavier, who's got that heavier total mass. Okay. so we'll do this next one. A batter hits at 37 meters per second pitch. Right before he hits the 0.145 kilogram ball, his 0.95 kilogram bat is moving at 25 meters per second. Right after the bat hits the ball, the bat moves at 15 meters per second. What's the ball's velocity right after it hits the bat? Okay, so I'll try to draw a before and after picture again. Hopefully this is in sight, yeah. Okay, so I'm going to say the ball comes in like this. This is our baseball. This is our bat. I'm just going to draw it as a square. This is 25. This is 37. Okay, then afterwards, the bat is moving this way at 15 meters per second, and the ball, after it hits the bat, is also going to be moving this way. We're looking for that, right? That's what we're looking for. Okay, so let me write down what we know, what we don't know. This is going to be a very similar problem. So we know the VI for the ball. Okay, I've got bat and ball. That's no good, because they both start with B. So I'm going to call this A. I'm going to call this B. So the ball has an A. The bat is called B. So VIA, that's our ball. Now, for this, not all of our velocity is in the same direction, right? This 37 is going this way. That's a lot different from a 37 going this way. So we have to account for that in our math, otherwise we'll get an answer that doesn't make any sense. So the way we do this is we take one direction, we call it the positive direction. I'm going to say that this direction is positive and this direction is negative. The other way you could draw this is you could say, oh, this is my x-axis here. It's important to have an arrow on the end, though. That arrow represents the direction that we're going to call positive. The negative is the direction we're going to call negative. What this means is that our initial velocity for the ball is going to be negative 37. Initial velocity for the bat is going to equal 25. Our final velocity for the bat equals 15. Our mass of the ball equals 0.145. Our mass of the bat equals 0.95. And we are looking for the final of the ball. Okay. Alright. So, again, same setup. The initial momentum is equal to the final momentum. So I will write down the expanded form of this. So it's going to be the same set of steps here. So M A V I A plus M B V I B is equal to M A V F A plus M B V F B. Cool. Now we plug in our numbers for all the numbers we know. So we know MA is 0.145 times our initial one is negative 37. It's important to have that negative sign there. You'll get a different answer. That'll be wrong if you have that as positive. MB would be 0.95 times 25. That'll equal 0.145 times VFA. That's what we're trying to find. And then plus 0.95 times 15. Okay. So now we know we're not going to have anything cancel out because we don't have a lot of zeros here. And at this point, it's just being careful and making sure that we put things into our calculator right. And let's see if my calculator is still alive. There we go. So we'll do 0.145 times negative 37. It's going to be negative 5.3. 37 plus, and then I'll multiply those together, so 0.95 times 25. 23.75 is equal to, and then I'll 0.145 VFA. Right, because I can't do anything else there. And then 0.95 times 15, we get this 14.25. Okay, so again, that's just plugging in, like doing the multiplication. Remember PEMDAS, so multiply before add. Then I'll simplify this side here. So let me do the 23.75 plus negative 5.37. So I get 18.38 is equal to 0.145 VFA plus 14.25. I'll get rid of the 14.25 on both sides. .13 is equal to 0.145 VFA. Then I'll just divide by 0.145 to get VFA by itself. And I get 28.5. Okay, so it's not like a great baseball hit, but it's kind of respectable. Might get like a single if you're lucky. Okay. This is an explosion one. Okay. So Gianna and Alyssa fill a tennis ball with gunpowder and light it. The tennis ball tears into two pieces. One's a 0.01 kilogram piece, and the other is a 0.045 kilogram piece. If the heavier piece shoots off north at 28 meters per second, how fast and in what direction does the 0.01 kilogram piece fly? So, in my picture, I will draw. There's like an explosion. Let me draw two pictures. First, we got the tennis ball. I think that's kind of what a tennis ball looks like. And then our second picture, we've got one piece shooting off north. And we're trying to find the other one. So then we've got, it looks like the heavier piece. So that is going off north, and then another piece is going off. I'm going to say it's going to be in that direction. I should draw a big arrow there because it's going to be going quickly. Okay. So the key for this is at the beginning, our velocity is 0. So I'm going to call this piece A and this piece B. So at the beginning, VI equals 0. So that would be VI for A and VI for B. So VI A equals 0, VI B equals 0. Again, that's just saying when the two pieces are part of the tennis ball, they're not moving. So they've got 0 velocity. That'll mean 0 momentum as well. Mass of A is 0.045. Mass of B equals 0.01. The final is equal to V final of A equals 28 meters per second. Okay, and then again, I've got to choose a direction to call positive. I'm going to say that north is positive. Okay, so I'm going to say that's positive. This would be negative. I'm looking for the final velocity of B. All right, same setup. So I get MAVIA plus MBVIB equals MAVFA plus MBVFB. Cool. These, I don't know why I do uppercase and then lowercase, and I shouldn't do that. Okay, then I'll plug in my numbers. At the beginning, the velocity is 0 for each one of them. So that would be, 0.045 times 0 plus 0.01 times 0 is equal to 0.045 times 28, because that's positive 28, plus 0.01 times VFB. That's what we're looking for. All right, so these are both 0. So that'll be 0. That'll be 0. We get 0 is equal to, let me do 0.45 times 28. 12.6. Let me see how we're doing on time. We're about at 20 minutes. I'm going to end it once we get finished with this problem. That'll be it for today, and then you'll have some problems that you'll be able to do on the problem set. So, like, go through this video, and then spend the rest of the class looking at that problem set and seeing which ones you can do. Again, you can work in groups. Yeah. So, 0 on this side would get us 12.6, because that's what those two things multiplied together is, plus 0.01 VFB. Okay, now I'm trying to solve this, so I'm trying to get VFB by itself, so I'll get rid of this 12.6 by subtracting it. 0.6, so I get negative 12.6 is equal to 0.01 VFB divided by 0.01. Okay, and then that'll end up being 1260, negative 1260 meters per second. They go to VFB. Did I do everything right there? 0.045. Oh no, I said 0.45 instead of 0.045. So this should be 1.26. 1.26, and this would be 126 meters per second. Okay, what does that negative direct sign mean? That negative sign means that this velocity is pointing in the negative direction. So we would say 126 meters per second south. That'd be our final answer, because it's got that speed. It's got to be going faster because it's the lighter piece, and then its direction will be the opposite direction of the first one, because they have to add up to 0, right? So you have to have a negative velocity if you're trying to add it to a positive. Like, you need a negative momentum to add to a positive momentum for them to equal 0. Okay. For questions on this stuff, you can either email me or you can wait till I'm back to ask them. Good luck. Hope you're all doing well, and I will see you next week.